So welcome everybody. Maybe let me put far away. Okay. It has been a tiring day yesterday, especially the dinner. So sorry for being so late this morning. We have also problems here with the beamer, but Fabio, as usual, solved everything.
Okay, so good morning. I'm Giulio, and today I will talk about results of a European project, a partial result of an European project we are working on in the last 3 days. I will talk to you about diffusion. So basically, how virus, ideas, innovation spread over a networked context. So imagine to model society as a network in which the nodes are individuals and the links among them represent connection, friendship, working relationship, and so on and so forth. And you want to observe and model how information, virus, and some kind of content spread over this complex structure, okay? So basically, there is a very huge literature on the topic, but the real problem is to devise a simple methodology to perform experiment and simulation comparing different kind of algorithms. So what we did here is to define a platform, a library, a visual environment that allow different kind of researchers, students, or users basically to play with these models and define new ones to test how different virus, different condition, initial condition impacts on the diffusion of a content of on a networking system. As I said before, this is a result of a broader project, which is Simplex. It's an Horizon 2020 project, whose aim is to keep together data-driven analysis, models, and participatory consensus from people to build up some kind of interactive exploratories. So basically what we want to do here is to close the loop between theoretical models and data-driven analysis to basically define novel way to analyze and to give insight on a specific kind of problems. In particular, in this 3-year project, the specific topic that were addressed was the disease spread, so how a content will diffuse over a network. As I said before, diffusive phenomena are basically everywhere, from diffusion of viruses to ideas to innovations. All these phenomena that basically look at how a content diffuses over a network is a diffusive phenomena. For instance, the study of how the SARS spread or how the H1N1 virus became an epidemic a few years ago is something that could be related to the analysis and can be modeled through the analysis of diffusive phenomena over a complex network. As I said before, the study in this field are very heterogeneous and move from computer science to physics to, immunology. So it's a very complicated field of research because there is a common ground for all the disciplines, but the terminology could vary a lot among them. So a unified framework that allow different kind of subject, different kind of users to communicate with each other and to try to simulate different models is something that is needed. Why we talk about network when we talk about diffusion? Well, classical studies assume a network-free context, so basically works in the mean field theory. They assume that all the connection among individuals, among nodes are present. However, this assumption is somehow a very simple one because it limits the real dynamics of the diffusion process. Do not take in account the connection that regulates the interaction among individuals is something that can cause an overestimate of the study or a simulation of this diffusion process. So in recent years, in the last 2 decades, basically some classic models were adapted to take in account the presence of a networked context. A network that, as I said before, bring together both the entities on which the epidemics, the information, the diffusion spreads, and also the relations. So basically here we want to we want to focus on those rules of diffusion of our infection that takes care both the target at the end of the diffusion if they are connected in a social graph. Every kind of diffusive process, of every kind of diffusive model that have been defined so far can be basically abstracted into different components. The first one is the statuses of nodes that can be experienced during the diffusion of the epidemics, for instance. And the other are the transition rules, so the rules that regulate the transition from different statuses of the nodes involved. As an example, take into account the SIR model. This is a very, very old model, one of the first compartmental models. In this model, we have 3 statuses, SIR. S stands for susceptible, I for infected, and R for removed. Basically, here we have 2 transition rules that allow susceptible nodes to become infected with a certain probability, if they are if in their neighborhood is present another infected node or a set of infected node, and another transition rule that model the fact that infected node, after a while, with a certain probability, can become removed and then stop their diffusive acts. Okay, so they are no longer entities that can somehow diffuse the epidemics, diffuse the viruses on their neighbors. As I said, this is one of the ancient models, one of the oldest models for diffusion of epidemics. So far, we have experienced a huge proliferation in this field, and a huge problem of this proliferation is that each algorithm is implemented individually by its authors and often shipped in not so easy way to be used from researchers. There are different formats, there are different implementation facilities, so it's quite difficult to perform a comparative analysis due to the fact that the technologies, the approaches are widespread over, for instance, the internet or over the publications. There is no easy to find a centrality point that collects them all and that allows to define new one with a standard framework, with a standard definition of input, outputs, and rules, and so on and so forth. For these reasons, we modeled this library, and we decided to populate it with a set of classic approaches and novel ones. In particular, we focused on 2 families of diffusion processes. The one is the epidemics, so those models that were devised to study how viruses spread over a complex system. And the other is the opinion dynamics one. Here, the topics of that is modeled is information. So, for instance, we want to model how a tweet diffuses over the social graph, or how an idea diffuses over a specific social context, and so on and so forth. This model can be reduced to the same pattern, basically, so statuses and transition rules. However, they are quite different in their basic assumption. For instance, epidemic models like SI, SIS, SIR, or threshold models assume that somehow the diffusion acts in a passive way. So nodes, individuals, cannot choose to become infected by a virus. It just happens, basically. You don't choose to get the cold, you get the cold, because someone around you has it already and pass you in some way. On the other side, opinion dynamics is something that model an active process of diffusion. So you see someone that retweet a content, and you decide if you like it, and if you like it, you can decide to share it against. So basically, this dualism, active-passive, is something that breaks down epidemics from opinion dynamics. NDLib, which stands for Network Diffusion Libraries, is not only a library, it's basically a framework. It's a service that is designed for an heterogeneous audience, so researchers, analysts, students, that comes from different disciplines, because as I said before, diffusion is a widespread thematics. So it's studied in computer science, in physics, in social sciences. And most importantly, these different backgrounds allow to research having different goals. So we have, for instance, the computer scientists or the physicists that define new models and want to test it against the state of the art, or simply students that want to learn a model or perform some experiment, or a social scientist that don't want even to code or to design a model, but want somehow to visualize the results, visualize some simulation to perform a proactive choice, a proactive analysis of a phenomenon. And the lib allow to do so in a very simple way, defining a simple workflow that can be usefully and easily adapted to different kind of users. So we will have a user that is a more technological user, a programmer, for instance, or a researcher that knows how to build up a model, to compute a model, to write down in code a model, and also an analyst. It could be a social scientist, it could be a student, could be somehow that doesn't have programming skills, but needs also to perform some experiment in this field. To both these kind of audiences, NDLib offers this very simple framework, this very simple workflow. Basically, it breaks down the problem of simulating a diffusion in two steps. The first one is selecting a network. It could be a synthetic graph, for instance, a Barabasi-Albert model, for instance, an Erdős-Rényi, or something that has well-known topological features, as also could be a real-world graph that is loaded in the system. After that, the second step is the one that allows us to define, to select the diffusion model amongst the ones that are implemented, or to define a new one, to configure its parameters, so define, for instance, in the SIR model, the probability, the transition probability from S to I and from I to R, and then run this experimental simulation. So once you have your network, you have your model or a set of models, you run this simulation, and you automatically visualize the results. So you can visualize, for instance, the diffusion trend, how the diffusion progressed through time. You can visualize the prominence of the various compartmental status. So you can see at each iteration which are the ratio of infected users. You can visualize how the length of the cascades, and so on and so forth. Or also you can visualize as a video, basically, how on the network structure progress the diffusion. This framework is implemented for both programmers and visual analysts. Programmers could choose to use this framework, this library, in two ways. The first one is basically writing code that works on their own machine. This is an example, for instance, of the SIR model that I introduced you before. As I said, in this Python code, and the lib is programmed in Python, you have exactly the step that I defined previously in the workflow. So you have this network loading phase. Here you use, for instance, Erdős-Rényi graph, then the definition of the SIR model, the configuration, and then the execution of several iterations. Indeed, in this example, the starting point of the infection are chosen randomly as the 5% of the node in the network. Indeed, the library allows also to finely tune the initial condition status. So you can specify the nodes that are infected. For instance, you want to test different settings. We want to test what happens to the diffusion if it starts from hubs in the network, so from very connected nodes, as well as if it starts from the periphery of the network, from nodes that are peripheral, that are very low degree. After the execution, once you have collected the iteration, with few lines of code, you can also visualize the results, as I said before. And in particular, our library offers two kinds of visualization. The first one are simple visualization that are bounded to a single model. So for each iteration of the model, you have this adoption trend, diffusion trend, prevalence trend. Or also, you can have also the comparison plot. So you can compare multiple simulation of multiple models in the same plot to observe, for instance, in this figure in the left corner on the bottom, how different models, for instance here an SIS, an NSI, an SIR model behave starting from a similar condition on a similar network over a similar number of iterations. Moreover, to test how different conditional status of nodes affect the stability of the diffusion process, we provide also a visualization that basically computes several instantiations of the same model with the same parameter, varying only the initial status of nodes. And this visualization allows us to see how is the median value of the diffusion trend, for instance, and the percentile bound observed around this median. So this could be useful to observe which will be the expected outcome of diffusion given a model, given the network, even overriding the initial condition of the nodes. The library is easily extensible. Basically, as I said at the beginning of the presentation, it abstracts each model by its two components. So the metadata describing the statuses of the nodes and the transition rule that describes how at each iteration each node can shift from statuses from another. And basically allow to define models in a very compact way. For instance, the more complex model that we have implemented so far is an opinion dynamics one developed by a research group in the CNR of Rome. It's a very complex opinion dynamic model that is controlled by about 15 variables. It's coded in at least 15 lines of code, so it's a very compact way to define models, a very simple one. And this extensibility allows us to somehow spread the use of this library to the usage not only of students or of analysts, but also of researchers that wants to have a common framework to model their diffusion processes, their diffusion works. The second way, and the lib can be used from programmers, is a more tricky one, if you want to say. So far, we have assumed that a programmer can work on his own laptop, on his workstation, and can write his code and perform experiment on his machine. However, often this is a very reductive way of imagining a simulation as experimental analysis. Indeed, some network could be very big. We are in the era of big data that are not easily analyzable in a simple machine. So what we did here is to devise a way to perform a remote experiment. So we transform our libraries in a RESTful service that allows the definition and the creation of experimental server. So how it works? It works in the following way. You have your experimental server remotely, for instance, in a research facility. Then you connect remotely from your laptop. You send out some instruction, for instance, load this graph, configure this model, execute this experiment, and the remote server at the end of the experimentation returns you with the results, the aggregated results of the simulation status, describing the simulation of the epidemics you have described. Upon this remote server is built the platform for the analyst, not for the programmers. So we build this visual platform that allow you to follow the same workflow of the programmer. So select a network, select a set of models, configure them, execute the simulation, all without writing a single line of code. So basically you have this web service that once loaded the network, visualize it. Once selected the model and configure them, execute the simulation, and then show you this animation on the network in which each node changes its color in base of the status is which, and the set of visual representation of the evolution of the diffusion. So you have the common diffusion trend diagram, prevalence trend diagram, and so on and so forth. Indeed, this is an open project. This is an Untitled, is an extensible framework, as I said before, that is not stuck to the model that we have defined so far. One first step, one first direction in which we are working so far to extend the library is to address a very relevant topic, the analysis of dynamic topologies. Recent works have started to focus their attention on coupling the diffusion processes, so the analysis of evolution on network, with the analysis of dynamic network topology, so the analysis of evolution of network. Indeed, assuming a static social context is something that is an oversimplification of the reality. Indeed, we have social ties that can vary through time. If we consider, for instance, a call graph, a graph built upon phone calls, the social interaction that occurs among the users is lasting only the duration of the phone call itself. So basically, if, for instance, we want to model the diffusion of information, diffusion of ideas that works through the call graph, we need to take into account also the evolving nature of the network topology, not only the diffusive process that works upon them. To do so, we have built another library, which is called Dynetics, that models dynamic networks. So it allows to define networks whose topologies change through times. And upon this library, we build an integration with NDLib that allows to define diffusion models that are specifically tailored to works with dynamic network topologies. Indeed, we are searching to extend our library. So if you have any kind of model that models diffusion on dynamics or static context, we are very happy to implement them and to ship it within our libraries. Also, the visualization facility offered are extensible. So any kind of novel visualization that give better insights on the diffusion processes is welcome. And finally, as I said before, this is a project this library is built within a project, an European project, which is Simplex. And within this project, other libraries and other visualization framework for diffusion of epidemics were devised. So far, we are working in this last year of the project to build up a comprehensive platform that keeps together all these different models, different applicatives. And at last, since we are also working in another project which is called So Big Data, this is a different kind of European project devised to the construction of an infrastructure. So the construction of a participatory platform for big data analytics. We are in the process of shipping NDLib, both the REST experimental service and the visualization one, as a tool that can be useful and can be accessed by researchers from all the world through this infrastructure, the big data infrastructure. NDLib is available, is a completely open source project, it's a free software, is a Python library, as I said before, that is hosted on the common platform, so on GitHub, on PyPy, that is the repository of Python packages, is documented online, and is already partially integrated on the So Big Data platform. So if you want to use it, to test it, to extend it, just follow this link and contact us for any questions. Well, that is basically all.
I just want to say that I find this fascinating, and in particular, as a non-data scientist, the possibility of what you can do and what you can find today. And I think that the point of today's debate is looking at how can these tools and how can this understanding help with supporting democracy. And I think following yesterday's debate, I think the question is also how can we ensure that these technology don't hamper democracy and we don't end up in a Black Mirror scenario. So I think this is a bit what we would like to pick up from yesterday and from your tool today. I had some questions in reference, actually, if you don't mind, and I apologize maybe for the stupidity of the questions, but this comes from a non. When you talk about the network topology, so the type of users and how you can see, how do you account for all the things that you cannot measure, let's put it in terms of data? And I've been working out with the Commission on impact questions, and one of the big problems that we always have is how much are we biased to actually measure and use the things we can measure as impact, as opposed to maybe asking the right questions, even though we can't measure them. Is this something that you feel can is a problem when doing these kind of studies?
Well, indeed, here the problem is that most of the models in literature are devised to be as generic as possible. So, to be applied to real case scenario, we have to move forward to extract and model some insight coming from data. For instance, a very nice analytical tool that were devised on another project, which is called GleamVids in particular. Try to do so by analyzing the network built upon airports, so flight connection, and tries to understand how, for instance, the diffusion of a virus is tied to the mobility of the users that carries them. Indeed, all these models have some limitation. They cannot account for external endogenous information, for instance, but they are just a proxy. Not particularly refined one, I have to say, but at least it's something to work with, to give some insights, to build up some observation that can be useful to make decision. And I think that's all basically. There is no solution, not an easy solution to embed real information into this model. Another kind of analysis is the one that is completely data-driven, but often these analyses do not propose an explicit model. They also observe something that is happening on a network, something that is happening on a social context. So there are two different kind of approaches. The one is trying to build some structure from the chaos, and the other is only trying to observe and to give some insight on what is really happening. We have to find a way to somehow couple them and to come out with data-driven support to model investigation.
No, because there's one thing that I find really fascinating when it comes to, and this relates to the recent British elections, where I think following the Brexit debates and everything there, where all the pollsters were actually wrong in guessing what was going to happen. There was a big movement within all the big polling agency of adapting all their models to this new reality, and actually they failed again to guess what was going to happen in the general elections. So I think it's very interesting. We have all this additional data and all these additional tools, yet we don't really manage actually to capture these data. So in your opinion, how close are we to these doomsday scenarios that have been depicted by Cambridge Analytica, where data can guess our decision-making process more than we can ourselves? So what is actually the reality of those kind of scare scenarios?
Smart question. Actually, there is a very nice field of research even tied to diffusion, which is quantification. So basically the idea here is to try to figure out which will be the shift in distribution of a content over a population. For instance, of an opinion, or another idea could be, for instance, looking at the employment rate in a population. We want to forecast which will be the shift in the future without saying you will be employed, you will be not. Just observing which will be the ratio among the two populations. It's something that will be developed in these years, in my opinion, and it is something that this data-rich environment we are living in will facilitate to analyze. But so far, in my opinion, real value of expressivity that we think our models have so far, and not the real, the actual expressivity they have. So they capture something that is not necessarily the reality. An example is the election in the UK. So the models predicted something, but in the actual context was the opposite. So basically, we need to define models that are more flexible to the variation, not dogmatic in their assumption.
Do you think we should open up to a proper...
Yes, I think so. So, questions from you? Oh, Marco.
So I just wanted to make a comment on the UK elections, and I think it's only partially true that pollsters got it wrong. It is true for the referendum. They got it wrong by a small margin, and it was enough to basically get it badly wrong. But for the elections, I think they realized that the problem was that they weren't accounting enough for the young people essentially not showing up at the polling stations. And if you look at the various detailed breakdown of the predictions that were made, there was actually only one of those who had a reasonable sample size and which adopted a reasonable correction for this effect, and they basically got it right. However, what they do normally is they weight all the predictions, and somehow this got lost because all the other ones had sample sizes that were 10 times smaller, and they got it wrong. So it's tricky, right? So details matter a lot.
Yeah, that's a very interesting point. That I think we shouldn't forget that, in some profound sense, social systems are not predictable. So the fact we can't predict them shouldn't surprise us, and we should understand that what this science is giving to policymakers is not definitive answers to any particular questions, but is an understanding of the problems and the possibilities. So in the case of the election, there were two outcomes which were well defined. It could go this way or that way, and then you had some view it was likely to go this way or that way, and people have to decide. But well, perhaps related to that, one thing that interests me very much in your presentation is that the way I see the world in this science is that it must involve everybody. So citizen engagement is important, but also engagement of the people in policy, people, you know, the officers of the European Commission or in the ministry or whatever else. And I was just wondering, I mean, this looks absolutely great, and the idea that you could take a non-technical person who doesn't want to read lots of manuals and stuff like that, and, you know, is it possible that such a person could engage with the kind of tools you've got and say, in an afternoon, actually have a working model or a graphic or something that informs the questions which interest them. So I was thinking, for example, in the UK and probably in other countries, we have a problem of health and welfare, how we're going to organise ourselves with an ageing population. And so if a civil servant was addressing that question, a non-technical civil servant, could they build their own model using the kind of tools you've got and get some kind of answer out of it?
Well, it's not so easy, but to some extent, yes. To some extent, meaning that if we provide some high-level definition of the model, some comprehensible definition by use case, by scenario, for instance, the SIR models that model this particular kind of transition. You have three statuses, susceptible, infected, removed. You give an overall idea to let the user able to choose a model, basically, to choose something among the existing one, and inform them how, tuning to numbers, to simple parameters, they can obtain different outcomes. Yes, I think they can use this in an afternoon. The problem here is to couple the overall general question to the problem itself. So the tricky part will be somehow let the user be aware of what is modeling, not how to use the model. Use the model is very easy by the visual platform. Just select the network, click a button to configure a model and execute a simulation, 3 steps, very easy. The problem is try to let them aware to what they are looking for. This is the huge step that will take more than an afternoon, basically, in my opinion.
I think one thing that's very interesting is yesterday we talked a lot about engaging with citizens, and I think that one of the things that we've been discussing quite a lot and that we're looking at now to do with the Commission is precisely understanding how people engage with the public discourse, because even though, I mean, I think it's very exciting what we talked about yesterday with Miguel, who was mentioning that, yes, but today we have focus group and we have a lot of different ways in which we can figure out what people think. And then we entered into obviously the difference debate between listening and maybe monitoring. And in my past role, we did a lot of citizen engagement activities where we actually asked citizens if they felt that policymakers listened to them. And of course, you can imagine what the overall view was. It was very, very negative. But we also actually asked if they felt that scientists were listening to the opinions of citizens, and that wasn't very positive either. The majority of citizens do not feel that experts listen to them or even take account of their opinion at all. And I think that this is actually an area where I probably feel that understanding better how opinion informed and who is talking to who and how you can actually engage better in this debate will be so valuable, not so much to brainwash or to manipulate society, but actually to see, well, who am I not reaching, or who am I not entering into a debate with, who disagrees with me, but I can still say that I disagree. And I think that this is one of the big tricks in trying to get democracy and digitalization together, is precisely not to think of digitalization as a way to manipulate or kind of abstract what people think, but actually enter into the debate. For instance, what we want to do with this, so we're planning to do a study where we're going to look at understanding how information flows on social media a bit better. And one of the precise things we would like to do is to say, for instance, once you have analyzed how people get information, etc., is also to look at what evidence is missing from the conversation, for instance, and how can you make sure that people get that evidence. So that you can actually build this discourse. So these are the things that I find really fascinating in potentially more than understanding what shall I do with this information, is understand what is lacking from the debate and how can you make sure that that is entered into the debate before you have a big referendum or decision. Because fundamentally, in a democracy, we think that decisions are made by the polity and it's by the common opinion. So, where do we go from what's the balance in the future world between freedom of speech and the right to access to information and the right to have all the information before you have to make a decision. I think these are some of the interesting questions that will come out in the next 10 years.
I would like to play the role of Miguel, that is missing, and respectfully disagree and spice up a bit the discussion. Otherwise,
Excellent.
we're all friends. I don't believe that scientists must follow public opinion.
That's
As
fine.
sharp as that.
I think that's fine. That scientists should do their thing. but
I'll
I
do an
think
example because I don't want to look bad. I mean,
You don't think policymakers should listen to public opinion either?
policymakers should, but physicians don't have to listen people who don't want to vaccinate their sons.
But if you enter
Period.
into the whole...
You know?
Now, if we're going to enter into the
Sorry, I mean,
contested debate of the vaccination debate, and it is actually really interesting because that's
I
been
want
a
to
debate.
space up.
That's been a debate that has been, if you look at the public discourse, that has been highly misrepresented, where the facts about vaccines have not been out there. And actually then I come to the point is scientists get upset that people don't want to have vaccinations and have these bizarre opinions about the dangers of vaccines. But why aren't they there talking to the public more about the stupidity of this decision of not wanting to? And I think that that's the whole, a lot of the debates around science, and particularly when science is highly misrepresented, it's usually because the people who should be in the conversation don't join, and so it's hijacked by people who have alternative facts perspectives. And I think that this is actually a very dangerous trend in our society, that actually experts move away from the debate.
As sharp as my... Yes, but we are touching probably the core of the problem. So I would call this the limit of democracy. So science is not democratic. So we cannot vote about the physics laws. I see all the people, so you see we spiced up. No?
You can't
And,
vote about physics law, but you should vote about the impact of this. So, for instance, with big data, privacy and privacy regulation, which has a huge influence for you.
A lot of people
is
now
going to be
instantly
debated.
want to discuss about that. So
Yeah, the probably model-wise, and that's also a question. In order to engage, possibly you can model the effect or the diffusion of two concurrent opinions. You know, so like the vaccination could be, let's say, the concurrent race between, let's say, whatever is fake and true news, which could be the knowledge about something or the ignorance about something. So the question is whether it is possible to model how or what could be the strategy in order to make some true news or vaccination effective when you have a contagion of a fake news. And so this would be the engagement from a science point of view in the effort to spread impactfully some knowledge throughout a large amount of citizens, right? So this is and this could be applied to every communication from a policymaker, from a politicians. Of course, the strategy depending on which kind of medium do you use, to which audience you refer. This could be, because in the model you see the two states, I don't see the third party represented. Thanks.
I think this is an extremely important point, and of course I respectfully disagree with you, or disrespectfully. This is an issue in the way that we are promoting global system science through our MOOC and through publications, the paper that I wrote with Ralph Dunn, that perhaps somewhat simplistically we make a division between, it's what Herbert Simon said, that the way the world ought to be, that is a normative thing. And in my opinion, that's not the business of scientists. That's the business of democracy or citizens or some collective thing where we get our collective value system says what we do. That in its purest form, the job of the scientist is to take information and to synthesize it and to say something sensible about the world we live in. But it's not the job of the scientist to say it's good or bad. So that in the example you give, if I don't vaccinate my children, a scientist can tell me that my child is more likely to catch some illness or die or whatever. Whether that's good or bad, that's not the scientist's job. That's the kind of collective social thing. And this is in our MOOC, and every time we present the MOOC, it gets a riot from the people who participate, and they say that scientists aren't as pure as that, and scientists have their own interests, and so on. And it is true that, you know, some scientists are lobbyists, but I guess my position would be that if you're a scientist and you feel strongly about something, get elected within a democracy, instead of abusing your power as a scientist. So, for example, if a rich person, if they use their money to promote some political end, then you may or may not think that is a good thing. And by analogy, we are information rich, and we can promote particular positions, moral positions, which could be an abuse of the power that we have. So I don't know the answer to this question, and if you disagree with me, that's great, come and tell me, and then try and get a synthesis, because I think we need to have a clear message, a clear understanding of this for ourselves, so that we can communicate it to other people. So, you know, so where is the position of scientists in policy? So what I've just said is that the one position is not establishing what's good or bad. That's not a scientist's job, that's a citizen's job.
Well, I disagree that scientists don't have a responsibility in science communication, because I feel that one of my key concerns when it comes to public discourse is that everyone else is out there talking. So I'm not saying that scientists should say this is the rule and we should everyone, but it's about promoting the evidence. Because in the debate in Italy about vaccines, you have doctors telling people that vaccines are bad for them. And then you have the scientific community that is not in the conversation. So of course, in that public discourse, and I think we're all citizens. Scientists are citizens, industry people are citizens, citizens, and I think everyone should join the debate without trying to bully, but I think the evidence and the lack of evidence, and we talked yesterday a bit about the UK Science Media Centre, which for me is one of the best examples of actually creating a structure that can help with this in a way to promote evidence without promoting one specific vision. So they don't have a political perspective, they're not for or against, they're just there to translate to journalists what science says. So what is the evidence, what is actually, and then the journalists can but it's a bit to make sure that journalists, and for them they work obviously with the big media, understand the science behind it. And a great example, don't you know if you remember, about 4 years ago, Seralini published his famous articles on GMOs, which became a big scandal in all of Europe, with the exception of the UK. The reason for this was the UK Science Media Centre. So practically, Seralini published an article in a peer-reviewed, well-respected journal, more or less saying that he'd done an experiment with rats and potatoes, GMO, and they had all died, and so GMOs must be terrible and they should be taken off the market, which is, of course, would have been a gigantic scandal and ruined the whole. So what did the UK Science Media Centre said? Of course, this is a really big piece of news. I don't know if it's true or not. That's not my point as the UK Science Media Centre, but I'll call the best people in the UK who work on this. I'll have them read through the paper and actually assess the facts. What they did is they actually saw a lot of errors in the process, and actually, you know, if you're given raw potatoes, nobody can digest raw potatoes. Human beings can't digest raw potatoes. So there was a bit of issues in the terms. So when the news hit the headlines in the UK, all the British science journalists had received a copy with people comments from Oxford, from Cambridge, from Imperial, with exactly what separate scientists, so it's not bringing forward a position, it's bringing forward 8 to 9 different academic positions on this paper, and it didn't become a scandal story in the UK. Some newspapers reported it, some didn't. Whilst in France, in Germany, it did become. And when I talked to journalists afterwards, and many in France and Germany, they were telling me, yeah, but we knew we didn't really think the story was right, but we have an obligation to the public that if a story like this is published in a peer-reviewed, reliable news, it is news. We have to publish it. Whether or not as journalists we think the science might be a bit strange, this is the role of journalists. And I think that that's when it comes important to thinking about what's the role of scientists in communicating the facts, is because if you're not there in the debate, other people will. And it's a bit when we were talking with Andrei Novak about looking at how can we bring evidence stories back into the public debate. And, you know, there's a big, you know, he would say, well, we can't plant stories, because that's how apparently the technical term, we can't plant stories because then we're interfering with democracy. I say, yes, but at the same time, everyone else is doing it. It's not as if industry isn't planting stories, or journalists, or the NGOs. And I say, if we can actually find a way to get evidence back into the debate, is that so bad? And that's a big moral question. What's the role of brokering evidence, or should we just leave it to everyone who has a political motive?
I'll pick this up offline afterwards. It's very interesting.
Other questions on this or other topic?
We killed it. Literally.
Too provocative, yeah. Well, on the other hand, there is a piece of good news. I saw the people with, you know, the pastries and the coffee going, preparing that. So probably we can end up here, even if it's a little bit in advance. But I don't think this is going to harm anyone. Okay, thank you. Thank you. Bye.
Thank you.